This is lesson 23, which is VHDL example 11. And in this example, we're going to take a slight diversion and talk about glitches. Now here's our 2-to-1 mux we've been talking about. You remember the truth table, you remember the Carnot map, and this was the circuit that we had. Now, let's suppose that A is 1, B is 1, and S is 0. That is, we're looking right here. This output should be 1. Let's see if it is. Here we're going to have a 0, the output of this AND gate. The output of this inverter is going to be 1. 0 goes to 1. 1 and 1 is going to be 1. So C is 1. And then we have 1 ORed with 0. So the output is 1. Sure enough, here we are sitting right here. Now let's make this S go to 1. Well, if it goes to 1, what happens? Well, now we have to remember that there are some propagation delays here. So let's suppose there's a 10 nanosecond propagation delay in each of these. So after this goes to 1, 1 and 1, this 0 is going to go to 1, and this 1 in S, the output will go to 0. And now we have a 1 and a 0 here, so another propagation delay later. This will go to 0, and this is already 1, and so this is still 1, of course. So propagation delay later, 1 or 0 is 1, so it's okay. So now we're here 1, 1, 1, so here we are sitting 1, 1, 1, the output's 1, no problem. But now let's see what happens if we bring the clock S back here to 0. If we bring it back to 0, what happens? Well, if it goes to 0, then a propagation delay later, say 10 nanoseconds later, what's going to happen here? We got a 0 and 1. This will go to 0, and of course this has to go to 1. So this goes to 0, this goes to 1. But now look, now we have a 0, 0 here, which 10 nanoseconds later, when it propagates through here, what will this become? Yeah, this will become a 0. Of course, this propagates too, but it's too late. This has become a 0. Now this goes back to 1, which means that 10 nanoseconds later, the 1 or 0 will become 1 again. So it should have stayed 1, but for a brief 10 nanosecond period it went to 0 and then came back to 1. That's called a glitch. Now we can actually use VHDL to simulate it. Let's write logic equations including these AND gates and inverters and OR gates from here. That is, let A, B, S be the inputs and Y the output. C, D, and not S, which is right here, will be these signals. And then we can say that not S is not S, and for simulation purposes we can write after 10 nanoseconds. That is, we can ask the simulator to wait for 10 nanoseconds before making not S not S. Similarly, we can say that C is A and not S after 10 nanoseconds. We can have D be equal to S and B after 10 nanoseconds. And finally, the output of the OR gate Y is C or D after 10 nanoseconds. Now, let's see what happens if we simulate this. We're going to set A and B to 1, like we had, and we'll make the clock go up and down. And this is not S, this shows C, this shows D, and here's the output Y, and look, here are the glitches. On the falling edge of this clock, just like we suspected, for this 10 nanosecond period, it glitches and goes down to 0 before it comes back to 1. So we expected Y to stay 1 for the whole time, but we get these glitches due to the propagation delays in the gates. Now, is there any way to get rid of them? Well, it turns out that the source of the problem is back in this Carnot map we had these two circles, and notice that they didn't overlap. You remember when we made Carnot maps we always tried to draw the fewest number of circles that covered all of the ones. There was this prime implicant here that we didn't need, but it turns out that's the source of the glitch. If we added this circle in so that there's no way to go from here to here without and getting the possibly a non zero showing up, we can add this term, which is just A and B. So if we added another gate in here, another AND gate that had A and B, and made it a 3 input OR gate, that should get rid of the glitch. And so let's try it. We're going to add this OR gate A and B after 10 nanoseconds. We'll call it E. And then Y is going to be C or D or E after 10 nanoseconds. And let's see what happens if we simulate it. Sure enough, the glitch goes away. So here's the glitch is gone. A and B are 1. The clock goes up and down, and we have no glitch. Now the question is this going to be a problem with us? Well, it's really not going to be a problem likely to occur. Glitches occur in FPGAs, or propagation delays, but there are a couple of solutions. First of all, you remember that in the FPGA we really don't have these gates, so we have just lookup table. But later on, when we talk about sequential circuits, we'll see that these flip-flops that we introduce only change on the rising edge of the clock. And in between that time we can have these glitches, but we need to wait for those to settle down before we sort of latch things in. So in general, we don't use Carnot maps anyway to solve our logic equations. We write these, as we've seen, these behavioral statements. But I just wanted to show you the source of these glitches and how sometimes they can occur.